Look at an example. We're going to let the interval xa to xb equals 0 to L. We're going to let c equal to 0, a equal to ea. So, of course, this is our bar problem again. All right. So Kij in that case goes from 0 to L. We have ei dni dx dj dx dx. All right, so you guys know I don't do algebra by hand. So let's go to trusty Mathematica. And I don't have any notes on this, so we're doing it live. All right, so the first thing we have to do is come up with the shape functions, right? And I could just write them down. They're really easy. We're talking about linears, right? They're really easy. So, but let's go through the process of coming up with them again, right? So we have some x that's our interpolation. So for linears, that would be 1 in x, right? And then we have this so-called A matrix that it's going to be x evaluated at the nodes. So there's 2 nodes in this example, one at 0, one at L. And our shape functions are then, and we want to make them, well, I'll just show you. Let me just do this first. Ah. What? What am I doing wrong? Huh?
Either x to the column or x to the
Oh, there's an extra set of parentheses in here. That's what it's doing. That's what's causing it. Let's try this. What the heck? Ah. This is exactly what I did last time, right?
What about the transpose?
That's not the problem. It's that I can't take an inverse of A because it's not a non-empty square matrix. So let me look at what A looks like. So okay. Okay. There we go. Sorry. Okay. So now I want my shape functions to be evaluatable at x. You know, they need to be functions of x, right? So if I just assign them to a variable, you know, then, you know, I can't. I mean, I could do a substitution later on, but that's not what I want to do, right? So what I can do is then I can assign these, and the syntax in Mathematica is, you know, like this, right? And it's probably because I've already evaluated it, but let me try this again. There we go. So now if I evaluate, you know, okay, let's do it different way. You can make longer functions in Mathematica by calling them modules. So this is just like function. So x and a are local variables. All right, let's go on. Let's see if that's going to work. Okay, sorry. That shouldn't have took me so long. That's what I get for not going through it in my office before I come and testing it out. Okay. So now I have a function that I can evaluate shape functions with, right? At different values, okay? And so then my K matrix is going to be the integral from 0 to L of EA d n x x d n x. You know what? I don't know if I even needed to do that. Let's go back. Let's just everything I wasted time trying to figure out, let's just get rid of. Because I'm going to integrate the x's now, so I think I just need dnn dx, okay, dnn dx. dx. Okay, but what I have there is not good enough because it's not. What I want is Kij. I want a matrix, right? And if I just do what I have there, dnn x is going to give me a vector, and dnn x is going to give me a vector, okay? And when Mathematica just sees two vectors, it's just going to multiply them element-wise. So I'm just going to get a vector that comes out of that. That's not what I want. What I want is a table, which is going to create a matrix, right? That's going to go I, j, where I goes from 1 to, you know, I'm going to say the length of nn, just to be general. And j goes from 1 to the length. Hmm. Sorry, guys. Let me pull this out and just see what's going on here. If I just do this, what happens? Okay. Oh, I had a typo right there. Ah. Okay, so in this case, I probably could have worked it faster by hand. But nevertheless, there's our stiffness matrix. Okay, and so if we write it down, we have AE over L minus AE over L, AE over L, AE over L minus. Okay, so that's K, and we're looking for unknown U1, U2, and that's equal to 0 and P. Right? Because the Q term, Qn, is P. Right? That's my external force at the second node. Yeah, I guess I didn't draw it, but you know, if this was node 1, node 2, right, for this problem. Okay. Now, can I solve this equation? Can I just write K inverse times that? K is singular, right? So what's a quick way to check if a matrix is singular? Yeah, so I can take the determinant of K, you can see it's 0, right? So we have to apply the essential boundary conditions. So the best way to, well, not the, let me say the best way, one way to apply the essential boundary conditions is to modify the equation that, so remember this is just an equation, right? This reads AE over L times U1 minus AE over L times U2 is equal to 0, right? It's just an equation. But is that true? I mean, U1 is fixed, right? So we want this equation to read U1 equal to 0. So how can I modify this to get that? And just put a 1 there, right? And in general, this is always the case. If you have an essential boundary condition, you can put a 1 on the diagonal. In this case, the first entry is the diagonal. But if it was the 18th entry of the matrix, you'd put a 1 on the diagonal and then a 0, or not just a 0. In this case, it's 0 because U at 1 is 0. But if U at 1 was a fixed value, then you put that value on the right-hand side. So, you know, to do this programmatically in Mathematica, we would say that well, if this is 1, 0, if no matter what U2 were, that would be multiplying by 0. Yeah. Yeah, one on the diagonal and all zeros. Yeah. Yeah.
And if U1 were not zero, then the U1 entries for the non-node 1 rows would also need to be zeroed out. So like if U1 were 5, then in row 2 of the stiffness matrix, you would have to put in the first column a 0.
So he means 1, 2, K1, K2, 1 would be 0. Right?
I mean, yeah.
But like in our case, it doesn't matter because U1 is
Yes, 0.
Yeah.
0 anyway.
But if U1 is a fixed value, non-zero term, then you should make sure that
The
that
columns
term
are,
is zero.
yeah, the columns are, yeah.
We can also
It-
change the zero value in the right-hand side of the zero to the value of the U1.
Yeah, yeah. I mean, so this should read, if U1 is 5, then this should read U1 0, right? 5 right there. Yeah. Yeah, so I modified the first row of the stiffness matrix, right? Now I can invert it. So now I can invert it. And I can multiply that by the force vector. And what do I get? This is the displacement on the right-hand side. And it's exactly what we know to be the displacement from undergraduate mechanics, right? But the advantage of doing it this way is that, I can now, instead of having just a constant area, I could have, an area that's a function of the length or something, right? Oh. I guess I need some A0, right? So this would be for like a conic section, right? Cross section or a triangular cross section. Then this would be, if AO was your original length at the base, and it went to a point at L, this would be the displacement, right? And yeah, and then you can you can go higher order, so we could go. So now we'll have we're going to do a quadratic interpolation with a midpoint node at L over 2. So there's our shape functions. Don't need to change anything here. Now our stiffness matrix is bigger, right? It's bigger because there's 3 nodes. Still singular. We'll modify the first row, and then modify our force vector. Right? And so this is the displacement at the center node, right? Which is 1/4 the displacement at the end, which sort of makes sense because it would be half if it was a uniform cross section, right? But I have a triangular cross section that has a slope of a half. So then it's 1/4 the displacement at the midpoint. Right? And this is the benefit then, of the finite element method, right? Is that now we can just go on. So then we could have one at a third. 2/3 L stiffness matrix is bigger because now we have 4 nodes. To modify the first. And so, you know, then we can go on getting a more and more accurate profile, right? And I mean, remember, this is a function, right? I multiply then my shape functions times this, and I can have the real solution. So these are the UJs, right? And so NN times UJ, now I have a function. I have a function, and that's my entire displacement field across the element, right? So this is far superior to those finite volumes and finite differences you've been using, right, where it's just a constant throughout any section, right? Here we have a function, right? And so far, all we've done is the so-called P refinement. We've increased the order. What we can do, and we'll do next time, is also we have the ability to increase the number of elements. Right? So we can use lower order interpolations and more elements. The thing we're missing is how to assemble those elements, right? So what we did today was for a single element, but when you break it up into multiple elements, now you have an element stiffness matrix, and those won't change. The element stiffness matrix will be exactly what we did today, but we'll also have a global stiffness matrix where you'll have contributions, because you're going to have, you know, when you have a domain, they're going to share nodes, right? Or two elements will share one node. And so the contributions at that node from the element stiffness matrix has to be added from each element into a global stiffness matrix, and that's what you solve. I suspect this is the analytic solution. Probably, for that cross section. All right, we'll stop there.